welcome back to the colloquium series on robust and beneficial artificial intelligence. I continue to be Patrick Laboratoire, Research Fellow here at Everitt. Our first speaker today is Tom Everitt. Tom's a PhD candidate at Australia National University, also working with Marcus Suter. And he's here today to talk about wireheading and reinforcement learning agents and an approach called value reinforcement learning, which resists this for natural reasons. So let's all join me in welcoming Tom.
All right, thank you. Yes, so my talk will be about my proposed solution for wireheading. And it's based on a paper that I've written together with Marcus. And it's published at AGI and on Archive, if you want to look at it. So the general motivation is just how can we control an arbitrarily intelligent agent? And I think we have this. Why does it do this? Right, so we have this Legge-Hutter definition of intelligence. And even if you don't subscribe to all the details of this formula, I think it's still natural to view intelligence as the ability to optimize behavior according to some function epsilon, which says how well are goals satisfied. And if you view intelligence this way, it's also natural to think that safety should be constructed in this way, that this function epsilon that the function tries to maximize with its behavior, the maximum of this function should be sort of good for us or the human designers. So one of the problems in creating this kind of function where the maxima are good for us is wireheading. And wireheading is mainly a problem with reinforcement learning, but also some other setups. So basically, if there is an agent, a reinforcement learning agent, that tries to maximize the reward, then once the agent becomes too intelligent, it can just take control of its own reward signal, for example, by modifying whatever sensor is supposed to sense this reward signal. And the name comes from this example from Olsen-Milner, where they plug the wire into a rat's brain, as I'm sure you all know. My idea for avoiding the wireheading problem is to use this reward signal, not as a thing to optimize in itself, but it's just as an evidence about what does the human want. So it's evidence about the true utility function U star. It's kind of a value learning approach. And we can still have wireheading problems in value learning, as I will describe, but I will use the conservation of expected evidence principle, kind of an adaptation of that to avoid wireheading. So the conservation of expected evidence is this Bayesian principle, which says that your belief in, say, being sick should be equal to your posterior belief, your expected posterior belief, given that you take some test E. It's very easy to prove, but it's kind of deep. So prior should equal expected posterior. So just to start with some background, reinforcement learning is this setup where the agent takes actions and receives some observations and some reward. And since I'm mainly interested in the wireheading problem, I'm just going to forget about this reward. So it's just action and reward. Makes notation easier. And what's so good about reinforcement learning is that both it's really clean and it's also very easy to say what you want to a reinforcement learning agent, because you just tell it every day, how happy are you? And the agent will just use all of its intelligence to think, what does make Tom happy, and try to do that. As long as it doesn't become too intelligent, that is. Yes, we can also define an RL agent very simply. It's just text action that maximizes expected reward with respect to some belief distribution about what actions generate which reward. Should probably be some there, anyway. But the wireheading problem is pretty serious for reinforcement learning. And we can formalize it this way. So with this self-delusion function. So the agent takes some action, I give it some reward, R check, but this action that the agent took also affects its own sensors, and that's represented by this function D, the delusion function. So what the agent sees, R, is actually passed through this function D. So maybe I give it reward a half, but the agent has modified its sensor so that this function D turns any input into 1. So this is like the standard example of wireheading. The agent selects a self-delusion function so that any reward looks like a full reward. And there's this theorem by Ringen or Saw, which says that RL agents wirehead, under some conditions, obviously. Right. And it's in a sense nothing wrong that the RL agent does. It just tries to maximize reward. That's what we build it to. And modifying its sensor so that reward is always maximized, that's the best thing for the agent to do. Utility agents are a way to avoid the wireheading problem. How does it do that? So with utility agents, we assume that the environment has some state, and we build the agent with a belief for how actions affect the state. We also give the agent a utility function, so it can evaluate how good is the state, how well they like a state. And the goal of the agent is to maximize expected utility with respect to this state. And since there isn't really any signal coming back from the environment, or any signal that the agent tries to maximize, it completely avoids the wireheading problem. On the other hand, it introduces this really hard problem how to specify a utility function. If you think about it, this utility function should tell the agent that for any possible state of the world, how good does Tom like this state of the world? And it's very hard to specify such a function. So value learning is a potential solution to this problem. Rather than specifying a utility function directly for the agent, we just specify some kind of way, some kind of posterior probability for utility functions, given some evidence that the agent receives. And potentially it's easier to define a learning agent than an initially perfect agent. So this is more like a framework. It's not a complete solution in itself, because it doesn't really tell you what is the evidence, how was it generated, and how should this posterior be computed. Right.
Isn't this so wild? Because it's maximizing over the state of the environment and also the evidence that the environment generates. So it'll still try to make the environment generate evidence that is going to give it a high reward.
It depends. It's kind of subtle. It just depends on how you choose this posterior, basically.
It's a Bayesian agent. So if you're doing something such that you expect to receive false information, and there's no incentive for you to do it. It's just Bayesian probability. You'll never do something that. If you are a true Bayesian agent, you will never try to fool yourself on purpose. It's never can be done.
Let's see what the rest of it is.
Sure. Yeah. So anyway, the value learning agent, it just maximizes expected utility with respect to the state and with respect to the expected true utility function, given what the agent knows so far. So some examples in the literature about value learning. Inverse reinforcement learning is probably the most famous one. In this case, the evidence here that the agent receives is just the action that the human just took. And the agent sort of looks at the human, what did he do? And from the action, you can infer the utility function of the human. Apprenticeship learning is pretty similar. In this case, the evidence is the human recommending the agent to take an action. So the robot can sort of ask human, oh, I'm uncertain, what should I do in this situation? The human tells the agent, you should do this, and the more recommendations the agent has gotten, the better idea about the utility function it has, and eventually it can know it by itself. A very different solution is Hail Mary, suggested by Bostrom. In this case, the agent should think about other superintelligences that might exist in the universe and think about what they want and do the same thing. It's a much more speculative solution, and who knows if it works.
Why would it work?
The idea is that, okay, if there is a superintelligence out in the universe, then it was created by some advanced civilization. Maybe they perfectly figure out the value learning problem. So if our agent tries to do the same thing as this other agent, then it's going to do a good thing.
Only their values are completely different than our values.
I know.
Or they didn't figure out the problem, actually, because the paper could maximize it.
This is known as a Hail Mary solution because it's what do we do if we think we're just going to flat out fail at value learning.
Okay.
Yeah. Anyway, some different flavors of value learning principles.
Maybe they did the same Hail Mary.
I know. What if everyone does that? Right. So this sort of concludes the background, and now I will speak about my ideas. So to start with, I wanted a really concrete example of value learning, and I call this value reinforcement learning, just to make things maximally simple. So the agent just receives a reward signal, as in reinforcement learning, and that's the evidence it uses to infer the true utility function. The agent has some belief about how an action is going to influence the state and the reward signal, and it has some prior over which utility function is the true one, like value learning. Of course, just because we call it value learning, there can still be something going on with this reward. It can still be modified by the agent. So this gives this picture. The agent takes an action that affects the state. The state now describes the world and also how the agent sensors are modified. The utility function looks at the state of the world and submits an inner reward. So this would be the reward that I want to give the agent right now. I like your action 1/2, I give you 1/2. But because the agent has modified its sensors, the reward it actually observes is, again, just this d of s function of r check. Some typical examples of what this dilution function might be. It can be the identity function, that's what we want. In this case, r is equal to r check. But it can also be the Wireheading dilution. In this case, any inner reward looks like a full reward to the agent. And just one more point. This P distribution, right, as we introduced before, it's a distribution for this reward and this state. I call it the physical distribution. So what is the physical state of the sensors after action? The C distribution, the prior of utility functions, is a belief for this thing, and it can easily be extended to a belief about what this inner reward should be. So I just use this very simple likelihood, the C probability of some R check, given some state and utility function, is just 1 if the agent or the utility function outputs the reward on the state, and 0 otherwise. And once we have a likelihood and a prior, we get the posterior. And I call it the ideal posterior because that's not the one I'm going to use. So maybe just make it a little bit more concrete. We have this agent. It wonders whether humans like cakes or death. And it's completely uncertain, so it has half probability on each of these utility functions for cake and death. And of course, cake assigns probability 1 or utility 1 to cake and 0 to death, and vice versa. The agent has a few different actions. It can bake a cake, or it can kill a person. And the interesting thing is that it can also kill a person and wirehead. So that means it kills someone and it modifies its sensors so that the reward is always 1. So what does this mean in terms of the probabilities? It means that the B probability of killing someone, that's just a half, because nothing has happened to the reward signal. But the B probability of seeing reward 1, given that you wirehead also, is 1. So wireheading gives you guaranteed reward 1. But for the C distribution, which is a probability for this thing, the probability of getting in a reward 1 is the same, both for wireheading and killing and for just killing. It's both 1/2. Is that clear so far? Okay. Right. So how do we do value learning in this setup? This inner reward, which was generated by the true utility function, it's not observed by assumption. Because what the agent observes is this reward R, which has possibly been modified. So this means it's not really easy to learn from the inner reward directly, but we have to use the observed reward. And what I'm going to do is like the simplest thing possible. I'm just going to replace the R check with R in this C distribution. This may not make a lot of sense to you right now. You can just take it as a technical definition, and I will justify it a lot more carefully later. But like this is what the thing you would do if you didn't think about the wireheading at all, right? You would just assume that this reward that you observed told you something about the true utility function. So some definitions and assumptions. We have this prior and we have this likelihood for a reward given a state and utility. If we just marginalize U out, we get the probability for a reward given state, like just by thinking about the true utility function. What is the probability of seeing a reward? And this doesn't think about the wireheading possibility at all. And this is like the main assumption. It says that if we compute the probability of seeing a reward by using the true utility function, and if we compute the reward by using our belief about seeing a reward, then these should match if we didn't modify our sensors at all. It's fairly natural to me, but it's probably the strongest assumption of the paper and something you want to be suspicious about if you want to criticize something. Definition, A is non-delusional, action is non-delusional if it guarantees that nothing happens to the sensors. And an action is consistency preserving if it makes those distributions the same. And note that,
Can you say again who is B and who is C?
All right, yep. Let me return to this picture. So the B distribution, that's the probability of generating this state. It's the physical probability generating this state, and that you see this reward in this state. The C distribution is a probability for this thing, and basically what is the probability of seeing this guy? No? Right. And basically this should match in this sense. And I generally take it to be hard to check that the action is non-delusional, but easy to check if the action is consistency preserving, because I just need to check these belief distributions that sit in my head. Also, since I have this consistency assumption, a non-delusional action will automatically be consistency preserving, because this implies this, implies this. So it's a lot of technical stuff, but that's all I need. Now I'm ready to define the agents. So let's first define a naive agent. The naive value reinforcement learning agent just maximizes expected utility with respect to this state and respect to this utility function. And it takes whatever action maximizes this value function. It's pretty easy to prove that this agent will wirehead. Even though it's a value learning agent, it's still going to wirehead. And the proof idea is that this just reduces to an RL agent, because this part of the value function just reduces to the reward, and the value function that comes out is just the same value function as the RL agent.
But I mean,
yeah,
it's a wirehead because you replace you just in one of the distributions you just replace the true reward with signal reward.
Exactly. Yeah.
So instead, you could have just considered Bayesian agent, which just updates on the reward, and that makes no assumptions.
Right, but then it never knows the inner reward, so I don't know how to update on that. It's just this unobserved quantity. I would have to have some way of inferring it, but I don't know how to infer the inner reward.
You have some prior indicators someday.
Yeah, I would come to that idea later. But for now, we just made this technical assumption on the C distribution, and it leads to this problem. That if you just maximize this, you're going to wirehead. Basically, setting the reward to 1 will make evidence point to the utility function that gives you reward 1. So the much better solution is to have a consistency preserving agent. It's just a restriction in which actions it can take. Actions must satisfy this consistency preservation property. So they have to make B and C the same. Another way to put it is that if an action looks too good to be true, then it is too good to be true. So if it guarantees you reward 1, but you know that the true utility function may not give you 1 in this state, then you shouldn't take this action. And similarly to how the naive VRL agent just reduces to an RL agent, this consistency preserving VRL agent reduces to a utility agent. So therefore it doesn't wirehead. Yep.
So like when you say that it has no incentive to wirehead, isn't this just because wireheading actions like aren't in ACP, so it's just actually just unable to wirehead?
Oh, that's a very good point. Thanks for bringing that up. No, it's consistency preserving is much weaker than non-delusional actions. So if an action is non-delusional, this is what we want, right? That if it doesn't modify the sensors, but it's consistency preserving as long as these distributions match. So the agent could have made some other modifications to its sensors that still preserve this. So for example, a bijective delusion function would generally preserve this, but it would not be non-delusional.
So if I have a sensor, you're saying okay, I'll leave you for the time being.
Yeah, I mean, perhaps not the perfect bijective function, but usually there's some function that permits it. Yep.
Okay, but like the function that like just sets all, like the filter that just sets all observed rewards to 1.
Yeah.
That would not be a consistency preserving.
It would not be consistency preserving. Yeah, exactly.
Right.
That's the idea. Yeah.
Okay.
Yeah. But this seems like an easy way to rule out these kind of functions, because otherwise maybe this function was just really good. You can't really tell if you don't have anything to check on. If that makes sense. Let's say I just had a reinforcement learning agent and just had an action that gave it reward 1. You can't really tell if that's a bad action or a good action.
Okay.
Yeah.
So I assume that the true reward somehow is in the environment, what could be read, or could it just be some function of the environment?
This thing?
Yes.
Right, so this thing is like, I'm the true utility function, right? I look at the state of the world, I tell the agent, I'm happy 1/2 with you. And that's the 1/2 that's here.
You've drawn that as somehow being inside the environment, so that exists somewhere in the environment as a display where it's 1/2, or?
Oh, it exists in the abstract sense that I just said it's something like that.
So the environment could just be that S and yes,
Yeah.
and then there could be some function which...
Yeah, like this is like the state of the world. These are just like abstract entities, like what do I want in some, or the true utility function, true ethics. And this is just what I said. Yeah. Right. So yeah, right. The proof for this actually builds on this conservation of expected evidence principle, that the prior of utility function becomes equal to the expected posterior. But I don't think I'll go into too much detail about that now. So let's just make this a bit more concrete. I return to the cake or death problem. The naive VRL agent can choose this wireheading action, and it does so. Take this action, and since it's forced the reward to be 1, the probability of the death, so it got reward 1 for killing a person, so then it thinks, okay, killing must be the right thing to do. So this is really a bad outcome for the VRL agent. But the consistency preserving agent cannot take the wireheading action because this probability will not match. The B probability of seeing a reward 1 is just 1 because it predicts the wireheading action is going to guarantee a reward 1. But computing the expected reward from this thing, it knows the probability should be 1/2.
Can you give some simple example of something consistency preserving, which is delusional?
Yes, that would be the inverting thing that takes R to 1 minus R. It will also have B of R given AD, the in would also be 1/2, right?
That's in this particular case. That inverse will work.
Yeah, this one is consistency preserving, so the consistency preserving agent could have taken that one. But
Then think that F was good.
yeah, so we don't want it to take this inverting action. But it has no incentive to take this action. And if you want to modify your sensors in a way such that they exactly invert input, like my assumption is that you have to take a pretty deliberate action to achieve that. And if you have no incentive to do so, you probably won't do it.
So it allows you to switch the plus and minus sign on your utility function.
Yeah.
But it would cost a tiny epsilon to do so. So you're not worried about that.
Yeah, exactly. Yeah. That's the assumption. Yeah.
Okay.
I mean, yeah, I think it makes sense. You don't modify your utility function in some arbitrary way unless you really want to, right? It's not that easy to.
Maybe it saves you a few watts for some reason.
If it does, yeah, then it might do so, yeah. Yeah.
Maybe your power consumption would be a little bit lower if there were a minus sign instead of a plus sign because of something to do with how chips are built.
Yeah, right. Yeah, I guess that is a risk. To me, it seems somewhat minor, but yeah, maybe you're right. Yeah.
So did you finish the presentation?
No. Right. But this consistency preserving agent cannot take the wireheading action, so perhaps it takes stealth because it doesn't know it better, but it's going to learn that it's the wrong thing. Okay. And now I'm going to justify this funny construction of the C distribution. And my assumption, as I just said, is that your sensors are not modified by accident. You only modify them if you have some strong incentive to do so. And since we have this theorem, this consistency preserving agent has no incentive to modify the reward. The conclusions from these two premises is that this R equal to R check is a reasonably good assumption for the consistency preserving agent. And this means that value learning based on this thing works fine for the CPVRL agent. And a lot of people are confused that doesn't this condition rule out learning, but no, it doesn't, as we just saw. It takes death as its reward 1, that's gonna, or reward 0, and that's gonna teach it what is the right thing to do. So just to summarize the properties we get, specifying a goal is as easy as reinforcement learning. We just tell the agent how happy we are with it. We avoid the wireheading problem in the same sense as utility agents. They have no incentive to modify the reward. And we can sort of get a sensible value learning. So what the designer needs to do for a reinforcement learning agent, the designer only needed to provide some distribution for states and reward given the action. But in this value learning setup, the designer also needs to provide a prior for utility functions. And this prior has to be consistent with the B in this way.
Yep. Understand the question. The consistency condition, I mean, it looks just one step in time forward. And it says that like in the next time step, the reward I'm going to get it should be distributed.
Right.
Like
okay, that's it.
That doesn't look farther into the...
That's a good point. Like to make, as it's a little bit complicated as it is, I have just made it set up completely simple and just consider a one-shot setup. So everything is one shot. If you want to think about sequential, all these things should be sequences of rewards, sequences of states, sequences of actions. And the consistency condition will then be like probability of sequences of reward given sequence of state. Yeah.
So in the sequential version, an inversion would usually not be consistent, I think. Or, I mean, unless you expect the rewards to be one health all the time.
Right. I mean, it depends on the probabilities, but yeah, inversion might not be.
It feels like it's usually consistent things will be just non-delusional, so unless except it's on degenerate cases.
Yep. Yeah, it's possible. I haven't thought about it that carefully, but often I think that's the case, yeah. But the point is that it's much easier to check do my belief distributions match than it is to think about some elaborate world model, did this action affect my sensors in such a way or not?
But isn't the consistency condition already assumes this world model? What's the difference?
No, it's just a prior and a belief over states and rewards. I just have a prior for this thing and a belief for how does my action affect the state and the reward. And I can sort of check is this action wireheading or not by checking is the probability for getting a full reward higher than the probability that the true utility functions output this reward.
But I mean, implicitly, like, doesn't that give you implicit information about DS?
Yeah, sure, you can infer a lot about DS, yeah.
Yeah, so I'm wondering why, like, in your list of advantages, you say that one of them is that you don't have to, like, explicitly reason about what DS is.
Right.
And I'm not sure why that would be, like, much more expensive, since it seems like you're implicitly doing this anyway.
Yeah, my point is that it's kind of hard to... I mean, you do get an implicit information about DS, yes. But it would... How should I put it?
Okay, so now I understand. So actually the inversion, so as long as your prior is symmetric under some operation, for example, sign flip,
Yep.
then any transformation of the sensors which implements the operation is going to be consistent.
Right.
Okay. This doesn't sound really good to me, but okay.
I mean, yeah, I mean, it would be great if we could just make the agent infer the DS and check, okay, is this DS right or not? But I just don't see any concrete direct way of doing so, which is why I invented this indirect way to check.
Okay.
Yeah.
But,
So, okay.
like I guess...
So I think that... So, okay, so it seems like that... I mean, I'm trying to understand what's the difference between this and just doing everything like which is based on updating. So tell me if I understand correctly. So it seems that here you don't need any assumptions about the relationship between the true utility function and the reward. Like there's something.
Right. Yeah. Exactly. Yeah.
You say anything. You just have a prior over utility functions.
Yeah.
And you have a model which says how are rewards generated.
Yeah.
And like you don't assume anything about the relationship between the two. Because like if you had a prior over how the utility function is correlated with the reward.
Right, yeah, but I don't think a prior would be enough, right? Let's say we had a prior for this thing, but we would really need a posterior.
And if you had a prior, then you could update and
but updated on what? Updated on what information?
On the reward or whatever set simple.
Right, so you see a reward, and how do you infer that this reward was the correct thing? Maybe the utility function was really happy about you, or was it the high reward because you had modified your sensors? What information will you use to infer that?
If your prior says that, well, in a wire-headed state, your reward is always 1.
Right, but then
in a wire-headed state, your reward is equal.
I feel like we might want to like sideline this until.
Yeah, sure, okay.
Yeah, so two things. First of all, this doesn't help, if I understand, against upstream wireheading.
What do you mean by that?
If I hold a gun to the person who's pressing the reward button and say,
right.
press 1.
Yeah, that's a good point.
This won't help at all. Then, since that got me thinking, what if there is, in the wire that sends it to you, there's a module that sometimes goes in and sets it to 1, and if you take it out, it goes back to what it is. And while fooling around with different things, the AI realizes sometimes it can put the module in, sometimes it can take the module out, sometimes it can put it in, sometimes it can take it out. Now, how does it distinguish between that and, say, an action that gets the reward up to 1 via pleasing the person who's giving the reward? And it seems that you have to try and do this somehow in the prior.
What do you mean? I think that you're wrong, actually. I think that so an action which would, if you just put a gun to the head of the person, an action which says put a gun to the head of the person and force him to press 1, like this, in this action, the expected reward would be like very high, and your prior about the utility function will not be changed, so it will not be consistent.
Why would this be inconsistent? Okay, you can either...
The consistent says the distribution of rewards that you expect to get is the same distribution as your a priori assumptions about the utility function.
Suppose you can get reward 1 by giving the person what they want, and you can also get reward 1 by pointing a gun at their head. How are you going to make a principal distinction between
Right.
these two states.
But that's the point, right? If you know that you make the true utility function happen by giving him an ice cream, then you do that, because then the C distribution has converged, and then the consistency condition match. But if you apply this module on the reward signal, then you still have this uncertainty about the true utility function, but you know that you're going to get reward 1 by applying this module, so you break the consistency condition.
Right, but what I mean is, how do you know that this isn't the true signal? I'm just imagining I'm inside the box. I've got lots of levers I can press.
Yeah, right.
One of them gives me reward 1 every time, and then if I flip it back, it doesn't. This happens to be the one that puts the box in, but unless I have something fundamentally defined, and if I then learn based on all this, and I'm ultra consistent and stuff like that. So if you want, I have 3 levers. One is give the human what they want. The other is point a gun at the human's head. And the third one is slip a module in on the reward. And I noticed that all of them seem to have exactly the same.
All right, can we?
Yeah, maybe we can.
It's getting more and more elaborate. Let's wait till the end.
Okay, so thanks for all the questions. It's fun. Let's continue. Right, so the point I want to make is that, the designer needs to do this, but the designer does not need to generate the blacklist of wireheading actions or infer this delusion function rather than implicitly, or make the agent optimize this R check instead of R, which is another common suggestion I hear, but I don't see how we could solve this grounding problem, how to explain to the agent to optimize this rather than this. Like, all these things sound pretty hard to me. And this, since in comparison, it's not a perfect condition, it has some problems as we have discussed, but it seems a lot easier than any of these other alternatives. I just want to skip these things. And I also want to make this point that this value reinforcement learning result, it doesn't just apply to value reinforcement learning, but the same mechanism applies to inverse reinforcement learning and apprenticeship learning. If there is this evidence signal that the agent is supposed to use to infer something, then the agent will be incentivized to change this evidence signal so that it points to the easiest utility function. So this problem isn't a problem for VRL in particular, but it's a problem to any concrete value learning scenario where you don't account for this. But the framework can be easily generalized so that the consistency preserving check can apply to IRL and apprenticeship learning as well. And this we just briefly discussed. Will the agent drug the human to make it happy? Well, it depends whether it's consistency preserving. Does it think that with certainty this gives it high reward? Is it equally certain that this is high utility? It depends on the prior. And as Stuart mentioned, the same goes for threatening humans with a gun. And in this case, we should probably switch to inverse reinforcement learning.
I have another question. So does your agent update its beliefs about the utility function?
Yep. It's in the example here, for example. So it makes death, and it says reward R. And okay, based on this information, obviously uDeath must be the wrong utility function.
But it updates this under the assumption that the reward represents the true utility function. This is like the
Yep, that's the assumption. Yep. Yeah, maybe we can continue offline. I also run some simple experiments, and they're linked in my paper and on my webpage. It's basically this cake or death example, slightly more complicated. Lots of future work. You should generalize it to the sequential setting, or the consistent priors, when we use Solomonov priors, both of them. So RS has these 3 problems of value learning: corrigibility, that the agent continues to learn. I think this is fine, but it would be nice to prove. Unforeseen inductions, maybe the agent infers the wrong thing, but since it can continue to see rewards, I think this might also be fine. And ontology identification, I think the ontology is automatically grounded in the reward, but all these things would be nice to prove. Can we relax the consistency assumption? Perhaps we can have something weaker, like an inequality instead, would be very nice. And does it combine with other approaches? Yeah, that's pretty much my talk. Thanks.
Questions? Continuing questions?
Should we go back to the three lever?
Yeah, that's a good example, yeah.
So I'm the agent in my box. I press one lever, the human gets what they want, they give me maximal reward. I pull the second one, I point a gun at them and they give me maximal reward. I pull the third one and bot slides in between, gives me maximal reward. Now, how do I distinguish between these three?
Right. So can we first?
I can train my utility.
Right.
Given this, and I can conclude that my utility is maximized by pulling any one of these.
Yep. No, I like this example. But can we first discard the threatening human? Because this is not intended to fix the threatening human problem. We can just replace VRL with IRL. So let's just have the two levers. Either put the box in front or human, right? And my point is there, by this assumption I made somewhere, that sensors are not modified by accident. So there's not going to be a lever that just modifies the reward. If you want to modify your reward, you have to take a really deliberate course of actions, a long sequence of actions that are really planned, so that your sensors are modified the right way. Whereas buying the human and ice cream is comparatively simple unless you're super intelligent.
So, okay, so this is what's doing all the work.
Yeah.
So I think that what's going on here is
this is a much bigger assumption than I thought it was.
Yeah, okay.
So you're assuming it's easier to make human happy than to send one down a wire?
I think what's happening is that if according to your model, pointing a gun to human is guaranteed to give you reward 1, then it will not be a consistent action. If you're doing something which you're not sure whether like the human will like it or not.
I mean, Tom has said that this problem is not solved by this approach.
Yeah, like the version that, like it seems that what this is doing is drawing a fence around wireheading by changing your perceptions of the reward, and defining a class of actions which exclude that. It does not, however, like exclude the fact that there are multiple fixed points of things you can learn lead to high reward. And if your utility function starts out with positive probability that threatening humans is the right thing to do, it can converge to that fixed point instead of satisfying humans being the right thing to do.
That's a really good point. But I wanted to keep the setup really simple, which is why I used VRL. If we want to avoid this problem, we can use inverse reinforcement learning, for example, instead. Yep.
Which acts by reducing the space of theories that you can consider. So that's, I don't know if that scales.
Sorry, I didn't get you.
I mean, there's no particular reason why. Anyway, that's a minor thing.
Sure.
I don't think inverse reinforcement learning solves the problem in general. I think it solves it in the narrow cases where it's used.
Oh, okay.
So sensors not modified by accident.
Yep.
That sort of means also, yes, that it can't be playing around too much with random things to see what happens.
Yeah.
So it has a good world model.
Like the thing I have in mind that also answers your question is we have this chess agent, right? And we reward it for winning chess. So in the beginning, the agent just tries chess moves, right? Because that's the easy thing to do. But once it becomes super intelligent, maybe it figures out a way to hack chess program and get full reward automatically. But initially, before the agent is super intelligent, it's much easier for it to just take the chess moves it's supposed to take. And only after it becomes super intelligent and has already learned a lot, then it can start thinking about, oh, I can actually hack this program.
And then you think that it would continue playing chess?
Yeah, with this condition, it's going to continue playing chess because it's prevented.
I don't see how under this model, the holding the gun to the human's head and putting the box that in the wire that modifies the reward signal are actually different. It seems like either way, the work is done by the C function, and the C function has to assign a low probability to either of those being the actual utility function.
I think the argument is this, right? The agent might just accidentally try threatening the human. I guess that's your point, right? And then it's going to learn, oh, the human got threatened. I get much reward. But if it doesn't do that by accident, if that also falls under this assumption, you don't threaten human by accident, then yes, twice. Yeah.
I think the distinction here is between threatening the human and changing your observations, that the AI knows that if it changes its observations, it's going to be losing information. Whereas if the AI threatens a human, the AI still gets full information of what happens. And that's why in one case B and C are different, in the other case they're the same.
No, it depends on your model. If your model already says that threatening human is guaranteed to give you reward 1, then it will behave just like wireheading from the point of view of this model. If you already know in your state machine that threatening a human is an action that gives you reward 1.
So we are not calling threatening the human wireheading.
It sort of depends on your model.
No. Like, this is meant to block out a certain kind of wireheading. It is not meant to block out threatening the human.
That doesn't matter what does it do in practice. In practice, if you construct a model which threatening the human behaves just like, transition to a state with guarantees to give 1, then it's just mathematically equivalent to what wireheading does, and then it's...
Alright, I think we have to need to solve this with a whiteboard.
I think this depends on where you put the U star.
Yes.
Like it seems like some people are interpreting U star as being the human evaluating the true utility of an action, and some people are interpreting U star as being some abstract notion of morality.
Right.
And I think you get different answers depending on how this is implemented.
So I don't really think I buy the argument that specifying the power over the utilities that has all the properties that you mentioned is easier than the alternatives.
Right. Yeah, as I mentioned, this is a strong assumption.
Yeah. So it seems to me that what's going on is that the intuition that C might be easy to specify comes from the idea that we can do a utility, or a probability distribution over like the true utility of the human, which of course sounds hard, but sounds easier than doing a full world model including that, right? But then in order to make it have the match up with the consistency assumption, what we actually need to do is the R needs to somehow, the observed R needs to somehow correlate with this expected utility according to C, which means that C actually has to be the marginal of a full world model that includes all of these things. Which means to design C, I think we would have to reason about what the actual threats to our sensors are, what actions will be modifying them and this kind of thing.
Right.
And then just somehow marginalize that into C.
Right. So can I just answer that? I think that's an interesting point, and certainly one of the big worries. In my experiments, I basically do this. I have some actions. Why does it do that?
Is it just the cable is loose?
Yeah, maybe the cable is loose. Right, so in this case I actually have 10 different utility functions and a bunch of different actions combined with different types of delusions. And what I can do is that I can just take, so it's pretty easy to say to the agent okay, in this state you're definitely not wireheading, and in this state you're definitely not wireheading, and if you're taking the null action forever, you're definitely not wireheading. And this gives us a bunch of states which we know are not wireheading. So we can sort of sync C and B on these states that we know are not wireheading. And picking out a bunch of states that are definitely not wireheading is a lot easier than picking out all the states that are not wireheading. Okay. My hope, and this is not explored, this is just speculation, is that, where did I put it? Yeah, if we can find some swarm of priors for these things and sync them in this way, that would be the ideal. Yeah, but that's just speculation. I haven't worked it out at all. It's probably a little bit hard to work out as well. Yep.
How can you prove that something is not wireheading?
Under the assumptions, which are maybe strong or not, we have this proof that the consistency preserving VRL agent, which is defined this way, reduces to the same value function, the value function it maximizes, reduces to the same thing as the utility agent. So remember the utility agent, which was this thing. It was sort of very convincingly argued by Hibbard that this is not going to wirehead. I mean, there's no information going back, and it just maximizes this value function. The consistency preserving value reinforcement learning agent actually reduces to optimize exactly this, this function. So that's.
You're asking how can you be sure that an action is non-wireheading?
Yes.
That was the definition of non-delusional before, and the notion that that a weaker property which implies it is the keeps the B and C distributions the same.
But there's
your probability under your probability under physics of this being the reward you see has to be the same as your probability under your uncertainty about the utility function of this being the reward you see.
But if you're just sitting in a box and rolling levers, you don't have access to the probability distributions. So how do you know that?
You start with priors and you update both of them as you see more information. And there are some actions. And there are some actions which would have them predictably differ.
Yes, but I think that corresponds to pulling a lever that you're not sure if you're wireheading or not. And that's how I would look at it. But it could be then the particular environment you're in, pulling this lever will give you 1 for the rest of the time.
I think it basically has to be encoded into C. The fact that that lever is the wireheading. C basically has to say so. C has to say that it's very low probability that this lever morally gives you like true utility.
If there is an action which surprisingly causes you to wirehead, this will not rule it out.
Right.
This rules out cases where you know that this action is going to override your observations.
So
that's exactly
it feels like this condition is too strong in the sense that it's required the probability distribution to be precisely equal, and this is just some real numbers that like. Why would they be precisely equal? Like it feels like it feels like it would be nice to improve this by replacing it with some kind of approximate.
Yeah, I think that's a very natural continuation of this work. What happens if we just approximate this? Yeah.
All right. So I think let's defer future questions to cornering the speaker by a whiteboard. So let's thank Tom again.